All right, so here we are on the 12th day of the Bronco Show, and we are going to play around with logarithms. Logarithms, part 2, Revenge of the Log. Okay. All right. The first thing, you will be using a calculator for some of this stuff. You will be not using a calculator for other things. All right. First thing, okay. The change of base formula is a very, very nice, happy formula. All right. So find me this, riddle me this, Batman. Give that to 3 sig figs. Three significant figures. Yeah, use a calculator. So we're going to use the change base formula. Change base formula. If you do not have a fancy-dancy calculator that has all sorts of crazy buttons on it, and most of them do nowadays, this is solved by using Rule 8 in your notes, which was log A to the B is equal to log base C of B all over log base A of B. I lied again. So C could be 10 or natural log. It doesn't matter. And in fact, let's do this. Everyone on this side of the room use natural log. Everyone on that side of the room use base 10 log. Your intermediate values will be different for the natural log people. Like if you just look at your numerator or just look at your denominators, what your numerator will be and what your numerator will be will not be the same number. But when you divide them out by your respective denominators, you will get the same answer. And did you? What'd you get? Okay, go to your calculator and type the natural log of 0.067 and divide it by the natural log of 3. That's what you people are doing. You guys are doing the same thing, but you're not using natural log. You're using the regular base 10 log. Okay, hold on. You got negative, say again? And what did you guys get with the natural log? Negative 2 point. Okay, yeah.
So when we're doing this, if our calculator can't change the base, are we allowed to use that?
It depends upon what you're looking for. For example, if you are being asked to do this problem, which just says, give me a number that you read off a screen, I don't care what buttons you push on the calculator to get it. But there will be times when there will be times where you're going to want to use this on an algebraic expression, okay? Like you're going to have to manipulate math using this. And in that case, the calculator isn't going to help you. You know what I mean? So my fear with answering your question with an affirmative is that the next thought in your mind is, well, then why do I need to know this formula? You do need to know this formula for other reasons, not just finding a numeral value. Does that make sense? Okay. All right. Now, we were talking about homework before this, so you can either find me afterward or look at the notes, but this was the first slide of new material, so you didn't miss anything instructional-wise. Okay. All right, so now we'll do a little bit of math, a little more math. Solve for G. See, got y'all thinking. All right, what's the first thing that comes to your mind? What do you see? I make it simple. What do you see? You see 5 squared. You see a 5 and you see a 5 squared. You got powers of 5 in there, okay? That's the first thing that comes to mind. So again, this kind of comes back down to that fundamental theorem of arithmetic. Okay, whether or not you're thinking about the fundamental theorem of arithmetic, it is the tool that your brain used. So we're going to make a substitution. All right, and now using exponent properties, this is 5 to the 2x. Okay. Now, at this point, this is where individual techniques, comfort level, flair, whatever you want to call it, come into play. Some people would look at this and say, hey, I got a 0 on the other side. Why don't I just move the 3 times 5x over to the other side, get rid of that minus, and then divide out by 5 over 5 to the x? You can do that. That's fine. So this is one chain of thought. And now, and also, because whenever you divide out something, you have to set it equal to 0 in order to not forget about it, okay? And the reason why that happens was always is kind of a mystery until you see the other way to solve it. Watch. Some people might say, all right, fine, I'm going to do this. Pull out a GCD. And now the zero product property says that either the first thing is equal to 0, or the second thing is equal to 0, or both, which leaves me with this. This is why 5 to the x is 0. Okay? And in fact, there's a third way to play this game. And it's kind of an intermediate step, which isn't really necessary in a problem this simple, but it's a very, very useful tool when you have really ugly stuff. Okay? And I'm just going to say a substitution, which turns me into a squared minus 3a equals 0. Now, it's nice because it makes something with fangs and teeth and horns and, goes bump in the night into something a lot simpler. This problem doesn't have really powerful venom. It's not a really disgusting, evil problem. But when you have something that's really mean looking, this is a really useful trick because it tames the beast. It brings it down to something simpler that you might recognize. So, like, these kinds of exponent problems are notorious for having crazy quadratics buried deep inside them that you don't see right away. And until you make a substitution, does it pop out that it's a quadratic or some other normal looking form. So even though this may not be necessary, it is nice to see, okay? Okay. Yes. This one here? Because here I looked at this guy as being 5 to the x times 5 to the x. So both of these fellows have a 5 to the x. So I can factor it out as a GCD, and that's him. Okay? So now, using our logs, a little bit of algebra, some arithmetic, we can find our honest to God answers. What is this equal to? What is x equal to here? Does this happen? Try to take the natural log of both sides. There I took an extra step there. I brought the x down and then divided out by log base 5. What happens? Try it. Go to your calculator and type in log base 0, natural log of 0, and see what happens. It yells at you. It says, no, I can't do that. So this does not exist. There is no answer there. Instead, we can go to this fellow. So natural log of 5 to the x equals natural log of 3. X equals natural log of 3 all over natural log of 5. Because I took my exponent down as a coefficient and then divided out by the natural log piece. That will give you an honest to God answer. And for giggles, I'll write the step. Because I see a few deer and a few headlights. So, and what is the answer here, by the way? It should be less than 1. And I'm thinking close to 0.6. 0.6 what? 683? Good guess. All right. So, let's try another. Math. All right. Try this one, boys and girls. Riddle me this, Batman. Do this one on your own. Similar. Okay. So 9x becomes 3 squared x minus 3 to the x. 8, 3 to the 2x minus 3 to the x equals, okay. Are we cozy, comfy? Right, wonderful. Now, you can go ahead and say, you can do this if you're cozy with it. And that becomes okay, some people were doing this. Any of the 3 ways that I just showed you are perfectly legit. It's fine. This is cool. And you know what? I do this even when I probably don't need to. Just because it, defangs the problem. It doesn't make it look as bad. And then you can kind of deal with it when it's, just a purring little pussycat in the corner. It's nothing. Okay. So now, a equals 0, or a equals 1/8, right? And now resubstituting, and so and that's approximately negative 1.8. 8 what? 8, 9? Close. Close to what you're dealing with. Okay? Because remember, 1/8 is 0.125, and 1/9 is 0.11111. So they are really darn close to one another. Okay? All right. A little better. Want one more? This wasn't super hard. Aw. Where are my notes? I just put my notes down. Where the heck did I put my notes? What? What? Oh, there they are. Dane Bramage, Ronco. Dane Bramage. Okay. Here's a problem that I honestly, seriously think is really nasty. And the only reason why I bring it up, is because I actually saw one on a test. Saw one on a IB test. Not this problem, but something enough like it that it strikes my attention. Okay, this thing goes bump in the night. Okay, the thing that's scary about it is not the exponents. No. The exponents I'm not worried about. A thing that scares the daylights out of me here is the different bases. That's not, well, if it was plus, it would be a lot worse. If it was 4x plus 5 to the 4x plus 3 equals 10. But this is bad enough. I can't combine those exponents. I cannot combine those bases. I can't combine anything unless I have the same bases. So, what do you think? What do you got? And you have a 5 and a 2 on the other side. Well, it's 4, which is really 2, right? 2 2s. So, break it down to primes. Break it down to primes. Always break it down to primes. So this becomes right? And now I can bust up the right. And now it's not as bad as it looked. You see? Now it's not that bad. What do I want to do now? Divide. Put the 5s together and put the 2s together, because then you have bases similar to each other. See? Now it's not that bad. Now from here, all sorts of different things can apply. You can do this math in several ways that I can see right away. Yeah. The problem with, well, the right-hand side, sure. The left-hand side, no, because the exponents aren't the same. How would you fool with that, right? Right. So because you have the same bases, what can I do with my exponents? Yeah, I can subtract them all. Keep going. Don't let me stop you. Be the hungry velociraptor. Give me math, man. I'm making my prediction. So you're going to wind up with 2 to the something equals 5 to the something, right? Yeah. And then how do I get my x out of the exponent? So this side over here becomes 2 to the negative 3, 5 to the negative 2x. Yep. Negative 2x. Okay. And now we can take natural logs of both sides, or regular logs of both sides. Or you can turn this into 1/8. I don't care. However you want to do it from here. You could do this. If you don't like fooling with the negative in there, right? And now take a natural log of both sides. And from here, you're golden, I hope. Here, do this one from here on out. You don't need me for this. Did you get an answer? Yeah. Thank you. Mm-hmm. Yeah, that's about what I believe. Sure. Cool. And somebody yell out an answer. Almost, maybe, sort of, not really. Did you get that too?
Yeah.
Okay. Wait for a couple others. You got answer. Yeah. Say it again? Yeah, at the very end of it all, you're going to wind up dividing by the negative 2. Yeah, for sure. And when you play this game, you're going to wind up with the natural log of 1/8 all over the natural log of 5, which gives you some goofy answer. And then you're going to divide that by negative 2. I did it a little differently when I was doing it, because right here, I went off on a tangent and did because you took you take the negative 2x, you bring it down in front, and then you divide out by the natural log. Yeah, right. So when I got my answer, I got this. That's what I got. Yeah. Okay. I'm not quite sure I follow. Um, for example, these are some things you can do with exponents to make your life easier or better. You can do that's one thing you can do. For example, you can do that. And that would also work with a negative in front of it. Like that. You can do, yeah. Oh, on the other one? Oh, up top? Okay. Then you would have to have 8 well, you would have to have 8. The plus 3 would become an 8. Right. Did you get your final answer the same? Awesome. That's the beautiful part about algebra. All roads lead to Rome. Unless you're a Cretan, and then all roads lead to Crete. Anyway, so yeah, does this answer your question about exponents? Sort of? Give me some. 2 to the 9th. Okay? All right. This can become, well, no. Hold on. You could do this. Right? You can do that. And that's fine. You can split that guy up if you need to by using power rules. Because if you think about this going this way, it's a lot more comfortable. 8 is 2 to the 3rd. 3 times 3, 2 to the 9th. So you can go backwards if you need to. or forwards. All right? Okay. Good. Now, graphing them. Oh, that's a wonderful sound. All right. I made you a toy. Okay. So here is, this is my log to the base 5. This is the graph of log to base 5. I wanted to show you what happens when we change the base. Notice when the base is, if I can get it, 1. Just think about that for a minute. Base of 1. Okay, so there's a issue there. Log base 1 of, say, 3. And let's figure out what the heck that equals. No. Well, whatever it is, we're going to assume that it is a number, right? Whatever the heck that number is, it's equal to something. By the first rule of logs, this means 1, if I write 1 and multiply 1 times 1 times 1, how many times do I have to multiply 1 times 1 in order to get 3? Can't. Does not exist. So the log of base 1 can't exist. Okay? But notice what happens. It's kind of a neat. So if it's between 0 and 1, like it is here, it looks like this. And then if this thing kept getting bigger and bigger and bigger, that line gets tighter down in towards the axis. There is an asymptote. What is my asymptote? What's the asymptote? Yeah, the vertical axis, the y-axis. Okay? Because if I go from the right-hand side towards the x-axis, or the y-axis, I'm getting closer and closer and closer and closer to 0, but I'm going towards negative infinity. All right? Here, I still have an asymptote, and it's the positive y-axis. Still the y-axis, x equals 0. All right? Where is my logical operator? I'm missing some pieces here, people. Why do you do this to me? It happens whenever I take something off of. There it is. There you are. See, it disappears. And there it is again. I can't understand this. All right. All right. Sometimes I wonder why Java and smartboards just don't play nice. All right. There's my exponential. go. Can we all say, ooh, ah? So, what does this tell you? What do you see? Describe it for me. Not always. They don't have to. Here they don't equal each other. But what do you see? Nikki, what do you see? Yes. Inverses. They are inverses. How do you know that they're inverses? Right. They are symmetric about the line y equals x. Okay, some things to know. When you are finding an inverse of a function, and you did this in Algebra 2, you know that you swap the x and the y, and then you solve for y. If you want to make sure that you're correct, and you graph both equations, they should be symmetric to the line y equals x. Also, you want to make sure that your aspect ratio of x to y is 1 to 1. Or if you're working on a TI calculator, you want to make sure that you're going zoom square so that it actually is the same. So everyone go to your calculator, go and hit y equals. Hit natural log of x for y1, and then e to the x for y2, and then graph. Now, it doesn't look exactly like mine. In fact, it looks kind of swished out and dragged left and right a little bit more than normal. Okay? But if you really wanted to look normal, you could go ahead and go to zoom, and is it 5? Zoom 5, which would be zoom square. And yours should look like this now. Because this one down here, why does it do that? This is my natural log, and the other one is my e to the x. Okay? They are inverses of one another. Now, the really cool thing about natural logs is that if you give me a point on that e to the x curve, the value of that point, the y value of that point, is the slope of that function. So here, by the way, unless you have some sort of translation, what is that point always? It's the y-intercept, but what is the y-intercept always? Whatever the heck a is, unless a is 0. What is the y-intercept of that graph? 1. Because if you plug in 0 into this function, 5 to the x, 5 to the 0th, that's going to equal 1. So the y-intercept is always 1, unless I add something to it. If I add 2 to it, then everybody goes up, or everyone goes down, whatever the constant is. But the really cool thing about it is that this height is that guy's slope. Really cool. And in fact, it's really useful to everyone who's struggling through my HL2 course, because this is really useful in calculus. And this is actually one of the really neat properties of e to the x. Okay. Now, let's see. Okay. So, I'm going to graph the natural log of x. But what if you had to graph that? What could we do? You could take the 2 out, right? And now my function, sometimes it's easier just to do it from here, is that, where, and I kind of drew it poorly. That's better. Ignore that. Where that height is the same as that height. Because everything is doubled. So x squared, you can use the properties of logarithms to graph stuff. Okay? The height is always going to would be doubled. That's a hint. That's a hint. Okay? So I can use the properties of logs to simplify a graph if I need to. All right. Now, domain and range. What is the domain of the red curve? Domain is x is greater than 0. Wait. X element of the real numbers such that x is greater than 0. And my range? What's my range? No. What is it? Correct. Wonderful. Okay. What about... Ooh, word problems. Oh, sorry. Go back. They're all reals. Okay. Yeah, the script goes natural numbers, integers, rationals, reals, complex. And all right. Sure. Okay. All right, so I have a radioactive substance, and it's decaying, much like your attention. but probably is a little more massive. Mass of compound Oz has is dictated by the following. Mass of Oz is equal to 1,000, so I have a kilogram of it, where T is in years. Find out how much time it takes for it to for there to be half left. Mm-hmm. So my final mass is going to be 500, and solve from there. I'm going to leave it there. And this episode of The Ronco Show has been brought to you by the Natural Log.